All right, so let's continue with our work here on shear force and bending moment diagram. So again, we have cantilever beams. Now we have a uniform load. I'll help you a little bit try to visualize this. Remember that the concentrated equivalent for this would be what? W naught times L at a distance of L over 2. So that means the resulting moment would be in this direction, which is a negative bending moment, and would be WL squared over 2. And the shear would be positive and have a value of WL. So I am shortcutting the statics for the reactions, but I'm pretty sure you guys can get those. Everybody happy with that? So let's start with the shear diagram. So, what is the shear on the left-hand side, according to this? Positive W naught L. According to our diagram, the change in shear, our differential relationships, is the area under the load curve. So looking at this whole area, what is that area? W naught times L, but W naught is positive or negative? Negative. So if I start at W naught L and then change by adding a negative W naught L, I get to 0. Now what is the slope of the shear diagram? It's equal to the load. And what is the load? First thing notice is it's constant. It has a value of what? W. W positive, W negative. Negative. So I have a constant negative slope. So if I were to write that in, I'd have minus 1 to W naught. So I have a linear varying shear diagram. Any questions about that one? All right, so let's do the moment. So what do we know about moment? Well, looking at the left side, by the way, we always work from left to right because our relationships are set up for x going left to right. You can't start on the left side, on the right side, and move left. So what's the moment, the bending moment here at the left side? It's WL squared over 2, positive or negative? Negative. So I have a negative W naught L squared over 2. By the way, what's the moment on the free end? So I'd better get 0. Let's see if I do. So let's check. The change in moment is the area under the shear diagram. Now the shear diagram over the whole beam is triangular. The area of a triangle is 1/2 base times height. So 1/2 L times WL is WL squared over 2 positive, so that gets me to 0. What is the slope of the moment diagram? Well, it's equal to the load. Okay? I'm sorry, equal to the shear. Now, what is the shear starting at the left? What's the shear? It's positive, and it's WL. And what does the shear do? It decreases linearly to 0. Well, this is the easiest one. That means the slope here has to be 0. What does the slope at the beginning have to be? Positive. And if I actually penciled in the slope, what would it be? W naught L. You see that? So I'm going to start at a positive slope and decrease to 0. So that's how I can pencil in the shape of my diagram. Is this diagram exactly right? No. I just sketched it in. So this is where the concept of shear force and bending moment diagrams kind of slows down. Do I really care what the moment is in here? No. Not necessarily, because I already know where my maximum moment is. It's right there. And all I know is it decreases to 0, and it decreases how? What kind of curve is this? This is a quadratic curve, right? Constant load, you integrate it, you get one load up to linear, first order, You integrate it up, you get the second order quadratic. Remember, it's integral relationships. Okay? So, fire away.
I thought when you had a 0 on your shear diagram, your moment was at a maximum.
No. It just says that the curve has reached a maximum or minimum. This is a maximum value. It just happens to be 0. See, the curve is maximing out. See, it's peaking.
Okay. Yeah.
So shear cantilever beams are the ones that aren't nearly as intuitive. Now, when we get to simple supported structures, that will work out a lot better. So if you were to draw this curve, you would see that it does have a maximum value here, because 0 is larger than a negative number on the number line. But we're engineers. What does the minus mean? Does it mean it's less than something? No, it's just direction. No, it's a negative bending moment. Right? And that's different than a positive bending moment.
We changed that distributed load to a point load, correct? To get W, not L.
Yeah, that's just to help me find the reactions.
Okay.
But you don't draw it with the point load. You still draw it with the distributed load. This is just a quick help for reactions.
So why does the shear get smaller as it progresses through the
Because if you cut the beam and look at the right-hand side, say, and think of the shear counteracting this force as I move it over and over, how much force is there? Less and less and less to 0. You'll find out that in this course, the idea of cutting a section and looking at the left or the right-hand side is really the only thing you need to know how to master. Everything else is just statics. It'll help you with everything. Method of sections.
I was thinking of it this way, and tell me if this is sound or not, I guess. On the distributed load, I kind of think of all of those distributed points as individual points, and when you go down the beam, the moment's going to get larger and larger and larger, right?
No.
Kind of, and then that's why.
Actually, it's going to get smaller and smaller and smaller and smaller.
With a larger.
For the same reason I told Mr. Abney, if I cut the beam here and look at just the right-hand side, imagine the internal bending moment counteracting this force. And as I slide over, what is the force getting? Smaller and smaller and smaller and smaller, all the way to 0. Whereas if I cut it right here, I have all of this force to balance with the moment. Let's try this one. So again, let's try to find the concentrated equivalent force to make it easy to find our reactions. What would that be? What's the area of a triangle? 1/2 base times height. So this load should be W naught L over 2. And its moment arm from the fixed end will be 2L over 3. So with that information, I know that now my bending moment is W naught L squared over 3. And that my shear force is just that, W naught L over 2. So I know my starting moment. I know my starting shear. My shear is positive. My bending moment is negative. So let's start and build our shear diagram. So starting at the shear, what's the shear on the left side? Looks like it's positive W naught L over 2. Now the change in shear is the area in the load curve. So I look at the area in this part of the load curve. What is it? We've already noted it. It's WL over 2. And it's what? Positive or negative? Negative. So if I start at positive W naught L over 2 and subtract W naught L over 2, I get to 0. What's the slope of the shear diagram? What's equal to the load? So starting here at the left-hand side, what's the value of the load? 0. So that means I've got to start here with a 0 slope. Now the slope increases to a maximum value of W. And is that positive or negative? Negative. So that means I have a big negative slope of W naught. And all I have to do is kind of try to connect that. So there's my shear diagram. What kind of shape is that? It's a quadratic. In fact, it's a special quadratic. This is called a parabola because it has a 0 slope on one end. So believe it or not, there are some very simple formulas for the area of a parabolic section and its centroid. Why do I care about the area of it? When I do the moment, I need the area of the shear diagram. So let's work on that one. So what is the moment at the left side? Looks like it's negative W naught L squared over 3. What should the moment at the free end be? There's no applied moment, so it must be... Okay, so since this is a semi-parabolic section, the area of it is base times height divided by 3. And if you look in your book, this might help you in the dark of the night. Let's see if I can find it. I think it's in the back. So here is a semi-parabolic section. Notice it has a slope of 0, and it tells you the area is, it's 2/3 base times height. I'm sorry, not 1/3. And it also tells you the centroid, but we don't really care about the centroid. It also tells you the other part. If you were to make this a rectangle, the remaining part would be called a spandrel, and that's 1/3. It also gives you the formulas for any higher order, where n is the order of the curve. Hopefully we won't get to too many of those, but you might find this part useful. That's in the back flap of your book. So this is actually 2/3 base times height. So let's calculate it. So the change in moment should be the area of the curve. So 2/3 base L times height. And what do you know? You get positive W naught L squared over 3. So I have negative plus this area gives me 0. So let's do the slope. So the slope of the moment diagram should be the load. I'm sorry, not the load, the shear. I drew that wrong. It should be the shear. So what is the shear at the left side? It's WL over 2, but it is positive or negative? Positive. That means I'm going to start off with a positive slope of W naught L over 2 to 1. And I'm going to decrease to 0. There's my 0 slope. So now I'll just connect the dots and the lines. So there's my moment diagram. Again, the curve is not that important, except that where's the maximum moment? There it is. W naught L squared over 3, and the curve's at the fixed end. Where's the maximum shear? WL over 2 also occurs at the fixed end. So this was a linear line. This one is quadratic. This one is cubic. This is about the limit of what you can do with the shear force and bending moment diagram graphical technique. You can see when you start off with a linear function, when you get here, you got to worry about the area of a quadratic curve, and it may not always be parabolic. So it could be a challenge. So point loads and uniform loads are great. You can draw them very quickly and only have to worry about areas of rectangles and triangles. So any other questions before I stop this? Okay?